Hi everyone, I'm Manpreet Dash with Rheonics. Today, we are going to discuss how real-time viscosity management can transform coating processes in terms of quality, profitability, and sustainability. I will briefly introduce ourselves. Rheonics is a global automation provider of robust plug-and-play instruments for viscosity and density monitoring. Our products are based on technology developed over 3 decades at ETH Zurich. Our viscometers are used in a wide range of industries, including many coding applications. In this presentation, we'll share some information about our viscosity automation technology, how it can automate the coding process, and transform it sustainably. These are the topics I will cover in today's presentation. First, we will discuss the importance of viscosity in a coding process. Next, we will review how that measurement is made in the industry. Then, we will take up how an inline advanced viscometer can provide a path to total automation for controlling viscosity in coding operation. Lastly, we will discuss the technical, business, and sustainability impact of using this technology. Why measure viscosity in a coding process? Well, viscosity measures the rate at which a fluid flows under stress. It is an effective indicator of coating solids concentration and homogeneity of a formulation and influences key coating performance criteria such as paint transfer efficiency, sag resistance, and leveling behavior. A good composition alone may not be sufficient for smooth and defect-free coatings. Some of the coating characteristics that are directly influenced by viscosity are film thickness and deposition, finished surface qualities, stability, adhesion, color match, thermal and chemical characteristics. Few examples of coating operations where viscosity plays a crucial role in the application are battery electrode coating, automotive coating, anti-corrosion coating, coil coating, wire coating, contact lens printing. Most defects in coating can be traced back to incorrect viscosity. High viscosity can be problematic in application and deposition, whereas low viscosity can potentially lead to problems in sag and leveling behavior. These are a few examples of such defects. In this slide, the causes of such defects are listed. The frequency of these issues can be reduced with viscosity management. Let's consider one example of motile surface. It's usually caused due to inadequate mixing. In such a scenario, continuous viscosity data could enable real-time track of the mixing process and provide insights for any potential corrective action. In general, continuous real-time viscosity data can help show large deviations in the fluid, identify and flag up anomalies for operator to intervene and avoid defects such as orange peel, color variations, solvent pop, and blisters. The simplest and direct way to ensure that the coating operation delivers the desired quality is to ensure optimization for correct viscosity, which begins with reliable measurements. Once the correct viscosity has been determined, maintaining it consistently is key to success in the coating process in terms of quality. A closed loop viscosity feedback control system, as demonstrated in the slide, provides the foundation of an integrated viscosity management solution. We understand the role of viscosity in coding. Despite its importance to quality, viscosity is still measured by century-old methods that interface poorly with emergent Industry 4.0 standards. Resonance sensor and a predictive tracking controller technology offer a simple and efficient bridge to bring coding viscosity management up to the modern standards. But first, let's take a look at how viscosity has been monitored in coding process up to now. The two most prevalent methods to measure viscosity are efflux cups and rotational viscometers. These traditional methods of viscosity measurement are limited in their ability to supply the data needed for inline viscosity control. Are cups suitable? Let's understand how they work. Viscosity cups are filled with the fluid and the time necessary for it to drain from the cup is recorded. This time gives viscosity in cup seconds. But there are many uncertainties in procedures. Where do you dip the cup in the tank? When do you start and stop recording the time? How do you store the data and do long-term optimizations? These factors contribute to less than optimal accuracy and repeatability of cup measurements, even with experienced operators. Rotational viscometers and rheometers measure the torque necessary to turn a disc or cylinder at a constant RPM in a sample of fluid. The ratio of torque to spindle speed is proportional to viscosity, usually measured in centipoise. Neither of these methods is easily adaptable to real-time inline control of viscosity. The measurements must be recorded and entered manually into whatever automation processes they're linked to. Rotational viscometers are delicate instruments that prefer labs. By the time a laboratory reports on the viscosity of a sample, it no longer reflects the actual condition of the coating formulation in tank or circulation. As you can see here, there is a delay between measurement and action. The sample is collected from circulation and sent to lab for analysis. Lab measurement reports often arrive hours after the samples are taken. So you can only correct how the coating fluid was, but not how it is right now. Offline measurement methods are not suitable for use in a continuous production environment because they are not adaptable to real-time inline control of coating viscosity, which is affected by a lot of external factors. They are dependent on operator skills and interface poorly with automation processes involved. Rheometers and rotational viscometers need labs for analysis. There is a delay before the corrective action due to the time involved in the measurement procedures. Are vibrational instruments reliable alternatives? Vibrational instruments have the advantage of giving real-time inline measurements of viscosity, but each has its limitations, including difficult maintenance, easy to damage during installation and cleaning, tend to be heavy, bulky, and sensitive to damage. That is because they use vibrationally unbalanced resonators that need large counterweights to work accurately. Some are very sensitive to outer shocks and vibration. So what characteristics would an ideal viscometer for coating operations possess? Well, they're the following: inline real-time operator-independent measurement, maintenance and calibration free, accurate and repeatable, fast response, logs viscosity data, provide a secure path to full automation through automatic viscosity control. A balanced resonator inline viscometer meets all these requirements. It can be mounted directly in the mixing tank or a circulation line to give immediate real-time viscosity measurements. It has a compact form factor for easy installation. Its readings are independent of operator skill or judgment. It is robust and never needs any recalibration. The sensor fits in the palm of your hand. The inline viscometer can be easily mounted on the tank or in a circulation line without interfering with other equipment. It provides continuous measurements which show the instantaneous condition of the fluid once a second, as well as indicating its temperature. No interruption of the coating process to get a viscosity reading. As you can see on the slide, the picture on the right shows an inline viscometer fitted in an ink circulation line. Traditional methods interrupt the coating process and introduce delays between sampling and viscosity reading. The inline resonant viscometer measures viscosity and temperature in real time with no interruption of the coating process to pull samples or no delay between measurement, evaluation, and control. To recap, the advantages of the inline immediate viscosity measurement device. It replaces offline measurements using cups and rotational viscometers. It needs no recalibration, cleaning, or maintenance. Works with all types of coating formulations, solvent-based or water-based. It is independent of operator skill, compact form factor, and temperature compensation of viscosity. Extremely dependable and reliable data. It integrates seamlessly into existing coding environments. There is no need to redesign equipment to accommodate the inline viscosity measurement device. The real-time instrument enables a data rate of 1 reading per second. The proprietary software measures, tracks, and logs every variable. Data is available to the PLC and factory data acquisition systems. Plant managers, quality personnel, and production supervisors get powerful interface to directly view process data or to review it through process logs. Here's a typical use case of the inline viscometer in a coding environment. Sensor reading shows when the coating formulation gets thicker due to evaporation. Operator compensates immediately by adding thinners. Software shows the trend of coat viscosity. Operators can take corrective action if viscosity deviates from control limits. The viscosity data is displayed and logged for analysis and data-driven quality improvements. Measurements are in digital form, so the viscosity can be recorded and entered into the factory automation system without any human intervention. Let's discuss the first integration option. The viscometer probe can be installed in a mixing tank or in a circulation line. The sensor is connected to its electronics unit, which can be integrated into the tank mount or by means of a cable for remote installation. In this first integration option, the sensor is connected to the customer's PLC by any one of a number of interfaces. The PLC is programmed by customer automation engineers to fit the specific measurement and control requirements of the customer. A solenoid valve can be controlled by the PLC to dose thinners, paint, ink to correct viscosity. Another option for integrating the inline viscometer in coating process is the coating tracking and control system. It's built on three main pillars: the inline viscometer, controller, software with an intuitive interface. Let's see how this closed loop feedback system works. The inline sensor provides continuous viscosity readings, which are provided as input for the controller. The predictive tracking controller provides signals to open valves to dose solvent to the mixing tank. The intuitive operator interface allows one-click setting of viscosity. The controller actuates a valve system that accurately doses thinners into the tank as its viscosity rises due to evaporation. Its small, frequent dilutions reduce viscosity variations to an absolute minimum with a uniformity and accuracy unmatchable using cups or rotational viscometers. As you can see on the plot, the green line is the set point for the viscosity, and the red lines are the upper and lower control limits. The black line is the viscosity. This system keeps temperature compensated viscosity variations restricted to less than 0.2 millipascal seconds throughout the complete job. This is unattainable with any other instrument. This system helps unlock full automation in coding viscosity management. The controller is equipped with the most advanced process control features and interfaces. The operator can choose a viscosity set point from the touchscreen interface and lock the system to that set point. In the picture on right, you can see inline integration of viscometers in coating circulation lines. For a standalone or integrated viscosity control solution, there are many advantages. We are highlighting typical advantages of a good system. So how does this improve coating quality? An advanced system's high precision and accuracy ensures minimum fluctuations in viscosity and a tight control within set points, which results in a consistent quality. How does the system overcome problems of increased solvent consumption and emissions? The fast responsiveness of the system due to a superior algorithm ensures viscosity is brought back to within its control limits very quickly and with minimal dosing of thinners or solvent. There is no human intervention necessary. Finally, let's understand the technical, business, and sustainability impact of viscosity automation technology in a coding process. Technical: superior quality and consistency, track and trace of every job, Industry 4.0 connectivity enabling data-driven decision making and analysis. Business impact, higher efficiency and productivity with a faster automated system, reduced material costs, easy scalability, higher profitability. Sustainability impact, reduced scraps and rejects, lower solvent consumption and VOC emissions, safer and cleaner workplace, optimum material and energy consumption. On this slide, I'm highlighting some data on the reduced solvent consumption and emissions of a printing company which deployed the fully integrated viscosity automation solution. As you can see, they were able to achieve nearly 40% reduction in solvent consumption by using the system. The ratio of solvent to adhesive consumption went down after they deployed it in their laminating unit, and the same results were achieved when they deployed it in their printing unit. Consequently, there is a reduction in total emissions since the time this viscosity automation system has been deployed in the facility. You can see the plot on the left showing reduction in solvent consumption, and the plot on the right, the trend line in orange, shows reduction in emissions. So, viscosity automation has helped this facility stay well within the limits set by local and regulatory authorities. Let's try and understand the implications of adding just a little extra thinner on the environment. This is an example from an annual maintenance program to apply anti-corrosion coatings on steel. As you can see from the example, adding thinner, which is only 10% by the volume of the paint, can drive VOC emissions by as high as 40%. Therefore, a fast response control system which ensures minimal dosing of solvent can considerably reduce VOC emissions cost. To drive sustainability efforts, coating companies will look for continuing measures to minimizing solvent consumption in order to reduce VOCs and air pollutants. In applications where there is a possibility, they will seek alternatives such as water-based instead of solvent-based coatings. That means it's desirable for inline viscometers to work extremely well with formulations of any viscosity, low or high. How does an integrated viscosity control technology facilitate key automation goals? Viscosity automation can help in transferring the skill and knowledge of experienced operators to a secure automatic control system. The fully integrated solution removes the last barrier to full automation. It is easily integrable in any coating process and factory data system. Industry 4.0 compatibility paves the way towards data-driven decision making and fault analysis. Conclusions of this presentation: a reliable inline viscometer with an integrated control system brings coating viscosity control up to the standards required of modern industrial automation. It removes the subjectivity and long time delays of traditional methods, making possible inline real-time monitoring and control of coating viscosity. The integrated solution of viscometers and the control system improves both coat quality and consistency, reducing waste and rejects while streamlining the viscosity measurement and control process. Viscosity automation solution not only adds technical and business excellence to coating operations, but also transforms them sustainably. Thank you for your attention. We look forward to working with coating professionals and applying our knowledge of sensors to ensure data-driven quality control and greener coating operations.